So this can be read, for example, here is that when the truth was an additive model, we looked at only the top 50, we found about 20% of those additive effects. So essentially, if the black line is above the colored bar, that means p-values are more powerful. And if the black line is below the colored bar, it means that the random forest method is more powerful. And so just to zoom in a little bit more on this graph to make it more clear, this is where kind of some really cool stuff started happening. When the truth was an additive effect, the p-value method is a much more powerful approach. When the truth, though, is a dominant effect or a recessive effect, random forest is a much more powerful approach. And for those who are familiar with CART, this shouldn't at all be a surprise, because CART is notoriously very poor with when there's additive structure in the data, but really good if the truth is just a binary split in the data. So really what this is starting to suggest is that since each of these learning algorithms are going to partition the data in a different way, search over the data in a different way, they're each going to find probably a slightly different type of effect. The effects that are being found by random forest are going to be different than the types of effects that will be found by a p-value method, that will be found by a boosting algorithm, that will be found by anything. Really beginning to suggest that the best approach to working with this type of complex data is not just to say, I love this one method, I'm going to stick with it, but I'm going to try and do really work at it and try a lot of different things and see what I get out of it. Yeah.
Did you try heterozygous?
I thought about it, and in talking with my advisor, the biological advisor, she kind of thought that it wasn't really a relevant factor to look at.
We find with cognitive variables in schizophrenia, sibling, but the heterozygotes often have an advantage.
Yeah. And the truth is that's something that CART would do awesome at. That would be a situation where
it might do better than what
Oh, no, it probably would. Then it would really, because that's something that as a p-value model or any linear method you're not going to find, but a binary split you would very easily find. So just to kind of wrap up, the answers to those 4 questions posed, it does appear that random forest is just as good as marginal p-values in looking at top SNPs, but when looking at a larger selection, p-values do seem better. Gene importance does seem more powerful than permutation. There does seem to be a degree of robustness among the different M-tri values, though again it's much higher. You need a much higher value than you expect by default. And it does appear that random forest does pick up certain types of effects better than other methods. So just to kind of give a little bit of future work and some direction and some kind of pose some questions out there, so it does appear that random forest can be used for this data, but I still would pose out there shouldn't. At the end of the day, if we think back to what was needed with the empirical study, we needed to really get at the interesting results, we had to go through some subsampling procedure. And what the simulation results begin to suggest is that actually the subsampling, we would have done much more powerful, picked up more true effects, had we just started by using a p-value cutoff. And so perhaps a better approach would be some type of multi-stage analysis where we first did a screening via the marginal p-values and then use random forest to re-rank the data. And that's actually what I'm currently looking at right now, using different levels of p-value cutoffs, trying to see then what this essentially reshuffling can buy us. In terms of some future directions, I think there's a lot of interesting work that can happen with understanding the variable importance mechanism. And particularly, I think where there's the most room for innovation is trying to get at targeted parameters of interest. Remember, what we're interested here in this work, what we're interested in is the variable importance measure. The Gini and permutation importance were developed because they're very general and very easy to implement, work for any data structure. But here we're dealing with a very specific question, and we can really ask very specific questions of interest and get variable importance measures for them. We can get variable importance measures based on the joint distribution of SNPs. We can try and assess what is the causal effect, essentially, of different markers. So there's a lot of flexibility that can happen, and I think a very interesting area for future work. And I'd say a personal interest is really to try and move now beyond variable selection, but really understand variable and case relationships. I think it's kind of unfortunate, but one of the knocks on algorithms like random forest and boosting is that you don't get the nice pretty pictures that you get with CART. However, I think on the other hand, you get a lot more information through these dense tree structures where you can really begin to get at things like relationships between variables and case relationships. And there's a lot more information to be gained than just simply from a single tree. It's true that it's much harder to extract, but I think the potential is definitely there. So I definitely want to thank and acknowledge a few people. My advisor in biostats, Alan Hubbard, Adele Cutler, who has been wonderful as a sounding board and also in helping me write and develop my code, and then Lisa Barcelos and the Genetic Epi Lab, who are just a fabulous group of people to work with and know a lot more about biology than I will ever know.